Hey YouTube, today I'm going to teach you about the Laplace transform. Now, the Laplace transform looks like this. The Laplace of f of t is equal to the integral from 0 to infinity of e to the negative st. S is a constant. So it's not with respect to s or anything. Now, what is this integral? Why is it important? It's actually very important. So if you have a differential equation that's either, like, it can be nonlinear, non-homogeneous, can be non-separable, and you can't do like the e to the rt thing, then what you can do is Laplace transform. The reason that this helps you with these kind of differential equations is, well, let me show you. The Laplace of f of a function I'm also going to write as capital F of s, because this takes so long. I don't like the brackets, takes too much work. So, okay, of s equals, I'm going to do the Laplace of f prime of t, which is equal to the integral from 0 to, that was a bad integral, of e to the negative st times f prime of t dt. Now, with the f prime, I'm going to use the uv prime, so I'm going to make u e to the negative st, I'm going to make v prime equal to f prime of t, and I'm going to u prime would be a negative se to the negative st, let me move that away, and v would be equals just to f of t. Now if we rewrite this with the uv prime formula, we're going to u times v, which would be e to the negative st times f of t, minus the integral from 0 to infinity. Oh, and of these two, I'm going to take out this negative s, and so that would turn this into a positive. I'm going to put the s here, of e to the negative st f of t dt. And if you look right here, besides the s, this is exactly what the definition of the Laplace transform is. So I'm going to rewrite this as s times f of s. Remember, that just means Laplace of f of t, and because the s's are here, plus e to the negative st times f of t from 0 to infinity. Now, one requirement for doing a Laplace transform is the limit as f of t approaches infinity cannot, well, I think it can be infinity depending on the situation. It works for most functions. I mean, it'll find answers, but there might be some where f of t approaches infinity, but I don't know. So if you plug in infinity, you don't have to plug infinity here because this already is an integral. I just rewrote the integral. So since this is to the negative st, that would be like f of t over this. So this would just, I mean, let me think. Yeah, that would approach 0. Because again, f of t, if it doesn't approach infinity, so this would approach 0. So I'm going to write this as f of s plus 0 minus, and then we're going to plug in 0. So e to the 0 is just 1. So f of 0. So that is equal to the Laplace of f prime of t. Now the reason this is so important for differential equations is you have just broken down a derivative into a new function. This is just a random constant. This is 0, and s is also a constant. So you now have a regular function, and it actually breaks down the nth derivative. So the formula, I mean, you could keep doing the integrals if you wanted, or you could just take my word on this. I mean, the formula for Laplace of f to the nth derivative would be equal to, let's see, sorry, it would be Sn times, so again, this is Laplace of f of t minus k, I'm just going to make a variable k, n of s, n minus k times f to the k minus 1 of 0. All right, so this is actually the nth derivative Laplace. And if you do, oh yeah, I forgot to say, Laplace is also linear, so, because, you know, it's in the integral right here, so if you think about it, if f of x plus g of x, the Laplace of that would be the Laplace of f of x plus the Laplace of g of x, because you can just factor this and then separate it into two integrals. It also, coefficients like a times the Laplace of something is the same thing as the Laplace of a times something. So it follows those two properties that normal integrals and derivatives follow of the linear property. So this is a very, very important thing. Now, you can plug in a lot of other functions, and in fact, I actually have there's Laplace tables on Google, and I wrote down a couple of the more important ones, like sine. So these are the functions, and these are the Laplace. And it's actually really helpful to have a Laplace table, because once you solve for the Laplace function, you actually need to undo it. And so we'll be doing that pretty soon. So as you see, f and t, I kind of messed up when I wrote it, but here it is. And yeah, so here's just a couple functions. So let's use our Laplace transform to actually, let's use our Laplace transform to actually solve a differential equation. So I'm going to make one up like 3y double prime of t minus, I don't know, e to the 2t equals y prime of t. Now, this is obviously not linear because there's e to the 2t in it. Now, what you do is Laplace both sides, and since it's linear, it's the Laplace of this minus the Laplace of this equals the Laplace of this. So let's do that. So the Laplace of y double prime, again, looking back at the formula, or you can use the integral if you really, really want to. I don't know why you would, but I'm going to factor in the 3. So it would be 3s squared, the Laplace of f of t, same thing as f of s, minus s times f of 0 minus f prime of 0. Oh, I forgot the 3's. Okay, sorry. So that's the Laplace of this. And now we're going to do minus the Laplace of e to the 2t. So the Laplace of e to the at is 1 over s minus a. So a is 2. So that would be minus 1 over s minus 2 is equal to the Laplace of this, which is s big F of s minus f of 0. Okay, now we're going to solve for big F of s. Sorry. And let's do that. So I'm going to bring this over here and factor it out. So that would be s times 3s minus 1 times f of s. Yes. So a times f of s. So I'm going to cross these out because just in case I accidentally use them twice or something. And you want the function and its coefficient to be the only thing on this side, and you move everything else to the other side. So 3s, okay, so that would be equal to, I would add this over, so 1 over s minus 2, let me get that over, plus, let's see, 3s minus 1 times f of 0, and plus 3f prime of 0. And now we can just divide these to get the Laplace function. So equal to 1 over s times 3s minus 1 plus times s minus 2. Oops. So that's that, plus the 3s minus 1. Oh, that actually cancels out. So that would be f of 0 over s. Let's see what else we got here. Plus 3f prime of 0 over s squared, 3s squared minus s. I just factored that out and I didn't here. Okay, so now what do? Well, we got to inverse the Laplace, and there isn't really a formula to inverse it. So what you do is you look at a Laplace table and actually find the functions and remember the linear properties. So for example, 1 over s, there's f of 0 over s, and since f of 0 is a coefficient, you can just take that out. So 1 over s just goes to 1. So that means this is just f of 0. So we undo this, so now we get f of t. So we have f of 0 as the first term. Let me cross that out. So now this, I think the best way to go with this, because there's not many huge like fraction things, I would probably do partial fractions, and I'll do that in my head. Okay, so the partial fraction of this one is 1 over 2s minus 9 over 5, 3s minus 1, I believe. Yes. And plus 1 over 10 times s minus 2. Okay, so we got all that. Yeah, it was kind of big of a thing to write, but we got it. And plus, now it's partial fraction this, so that'd be 9f prime of 0 over 3s minus 1 minus 3f prime of 0 over s. Okay, so now we can inverse Laplace all of these. Oh, crud. This is, I didn't even inverse the Laplace yet. So I'll still write f of 0 over s, because I only inversed this one. Okay, that's fairly stupid. All right, now we can get to the inverse. So now we got f of t. So the inverse is f of 0, f of 0 over s is just f of 0. Okay, so we got that. 1 over 2s, which would just be 1/2 times 1 over s. So that'd just be 1/2. And then minus, and then let's see here. That would be, let me think about that. Let me click on thing on my computer to make sure it's right. Okay. So that would be what in the world? Where am I? Okay, so so that would be e to the t over 3, right? Yeah, t over 3. Again, I'm just looking at tables to undo it. T over 3 times 3/5. Yes. Yeah. Because you take, that would be 1 minus 1/3. So it'd be 9/5. Oh, okay. So that'd be 3/5 times s minus 1/3. Yes, okay. So we got that one done. Oh, I accidentally skipped. Oh, okay. Got those. And 1/10 s minus 2. That would be e to the 2t. 1/10 of that, sorry. And 9 times 0 over 3s minus 1. So so that would be 3f prime of 0 times 1 over s minus. So that would be e to the t over 3. Yes. E to the t over 3 times 3f prime of 0 minus, is that an s? Yes. So minus 3f prime of 0. Yes, that took quite a while. And now we can simplify this out. Let's set some initial conditions to make it cleaner. So f of 0, let's just make it equal to 0. And f prime of 0, let's make it equal to 1. So that would be f of t is equal to 0. Is that the only f of 0? What the? I feel like one of these should not have been f prime of 0. Oh, wait, no, never mind. All right. Okay, sorry. I was just confused for a minute there. So 1/2 minus e to the t over 3 times 3/5 plus e to the 2t times 1/10 plus 1, so 3e to the t over 3 minus 3. So again, we'll simplify that more. So f of t is equal to, see, so 1/2 minus 3, which would be negative 5/2. Okay, and so 3 minus 3/5, so that would be 15/5, 12/5. Yes. Wait a minute. Sorry. 3 minus 3/5, so that'd be 15/5, 12/5. Okay. Plus 12/5 e to the t over 3 plus 1/10 e to the 2t. And that solved this differential equation up here. And that is how you do a Laplace transform. Thank you for watching.